Hello everybody, my name is Pitones and I'm going to be solving Griffith's problem 2.12. The problem asks us to do the following. To use Gauss's law to find the electric field inside a uniformly charged solid sphere, charge density rho, and to compare our answer to problem 2.8. The first thing we're going to do is draw out Gauss's law, or write out Gauss's law which is this closed surface integral of the electric field dotted by the area element dA. And this is equal to the charged enclosed over epsilon naught. And to get a better picture of what we're going to be doing, I'm going to draw out our uniformly charged solid sphere, and I'm going to draw our little Gaussian surface. Our sphere, our solid sphere, is going to have radius big R, while our Gaussian surface is going to have radius little r. And so getting back to our equation, we should know that the charged enclosed inside of our Gaussian surface is going to be equal to the following. Equal to the charge density rho times the volume element d tau. And because it's multiplied by d tau, we're going to be dealing with volume integral. Also, now that we have this, we're going to be able to plug this back into our main equation when we're going to be solving for it. And before we do that though, I want to take out the electric field from this integral. And to do that, we're going to have to use symmetry arguments. And so the sphere we're dealing with has a uniform charge distribution, and this means that the charges are spread out the same in every direction from the center, right? And so because of this, this also applies to the electric field. And so the electric field is also spread out the same in every direction from the center. And so here we have our electric fields. And so it's important to note that they all have the same magnitude. And importantly, although it doesn't look like it because one's pointing top right, one's pointing top left, and one's going down, they're all pointing in the r hat direction, which is radially outwards. And so we can break it down our electric field vector into its magnitude and its direction component, which is r hat. And so to actually be able to pull out our electric field magnitude out of the integral, we are going to have to deal with this dot product and the area element. Luckily for us, we know that area elements are normal to the surfaces they're on. And what's the normal of this Gaussian surface? Well, it's also the r hat direction. And so this actually just breaks down our area element into the following. Just dA times r hat. And so we know that the dot product between r hat and r hat is just 1. So we're just left with the electric field magnitude dA. And so now that we have this, and we know that the magnitudes of the electric field are all the same around the Gaussian surface, it's just constant. And so because it's a constant, we're able to pull this out of the integral. So we're just left with the surface integral dA, and because the the solid sphere is also uniform, this also means that we're able to pull out the charge density from our integral. So we're left with the rho over, remember not to forget the epsilon naught down here, times the volume of the solid sphere that's enclosed within this Gaussian surface. And so when we're doing the integrals, we get that E is equal to, or E is times the surface area of a sphere, which is 4 pi r squared is equal to rho over epsilon naught times 4 pi thirds times pi r cubed which is just the volume of a sphere. And so we see these terms are very similar. We're able to cancel out 4 and pi, and we're able to reduce the r cubed on this side and cancel out the r squared on this side. So doing a little bit of rewriting, we get that the electric field is equal to rho over epsilon naught times r over 3. But because we know that what we have right now is just a magnitude and the electric field is supposed to be a vector, we have to find out what direction it's pointing. But as we found out earlier, it's pointing outwards in the radial direction. So what we have is the electric field is equal to rho over epsilon naught times r over 3 r hat. So this is our answer for the first part of 2.12. And now what the problem wants us to do is to compare our answer to problem 2.8. We know that 2.8 puts the answer in terms of total charge, and we currently have our answer in terms of charge density. And so what we have to do is we have to solve for the total charge of this solid sphere. And we know that it's the total charge is equal to the charge density times the volume element. And don't forget, because it's multiplied by the volume element, there is going to be a volume integral. And so when we're solving for the integral of the solid sphere, it's not going to have little r as the radius, but it's going to have big R, because now we're dealing with the entirety of the sphere. So what we should get is 4/3 pi big R cubed is equal to Q. Don't forget the rho. And also, because we're still dealing with a uniformly charged sphere, we're able to pull rho out of the integral. Just rearrange it, and rho is equal to 3Q over 4 pi big R cubed. And with this, we're able to plug this back into our electric field equation, which gives us the following. Our electric field is equal to 3Q 4 pi big R cubed times R, little r that is, over 3 epsilon naught in the r hat direction. And so we see that the 3's simplify and cancel each other out, and this gives us our final answer, which is the electric field is equal to Q times a little r over 4 pi epsilon naught big R cubed r hat. And so with this, we're able to compare our answer to 2.8 because we solved the electric field in terms of the total charge. And with that, 2.12 is finished. So my name is David Pitones, and I hope you've learned something today. Thank you for watching.